binary trees are trees with exactly 2 branches. Let's define a class for the binary tree, which we'll abbreviate as B tree. It's a subclass of the tree class that we already created. So a binary tree is a tree that has a left branch and a right branch. Here's an example. It's important when there's only one branch, whether it's the left branch or the right branch, because binary trees are ordered and often assign properties to their particular branches. So in this tree, the whole tree has both a left branch and a right branch. Here's a leaf. This subtree has a left branch and a right branch, but this one only has a right branch. It has no left branch. How are we going to represent that when previously we just had a list of branches? Now we need a way to indicate whether it's the left branch or the right branch. The way we'll use is straightforward. Left branches come first, then right branches. If there's only a right branch, we'll fill the gap where the left branch would be with an empty tree. This E is some representation of an empty tree, and we'll have a class attribute in the B tree class, which just represents the empty tree as a tree with no label. A second idea is that every binary tree, that is, every instance of the B tree class, should have exactly 2 branches, a left branch and a right branch. We can achieve this by adding branches to each of the leaves that are both empty. So a leaf in a binary tree is not a leaf in a regular tree representation because it does have branches. It's special because those branches are both empty, and when both of your branches are empty, that means you're a leaf for the binary tree class. Now we can define our constructor, which takes a label and a left and right branch. By default, these will be empty. The particular empty value that we've defined as a class attribute of B tree. We construct a binary tree by just constructing a tree, the base class, using the label, and putting the left and right branch into the list of branches. To access the left branch, we define a property method, which means that we can write .left just as an attribute to get access to the left branch, which is the branch's index 0. And the right branch comes after the left branch. Therefore, to construct a binary tree, we say the label 3 is at the top, in this root position. To the left, there's a leaf, B tree 1. To the right, there is a larger subtree. Here we have the tree rooted at 7, with a branch that's a leaf 5, and a second branch, which is 9 and 11 to its right. We explicitly specify that the left is empty here in order to indicate that 11 is to the right of 9. Let's take a look at the code. Here's our tree class from before. The binary tree class just specifies what's different between binary trees and regular trees. This notion of an empty tree is specific to binary trees. It's there to make sure that every binary tree has exactly 2 branches. The left branch and the right branch are defined in the constructor. We check here to make sure that left and right are both either the empty tree or instances of the B tree class, so that we don't accidentally mix together binary trees and regular trees. Here are our property methods to access the left and right, and we have a new notion of being a leaf. A leaf is not something with no branches, but instead something where both branches are empty. The repr method just shows what to display, and now we can create a binary tree. So a leaf looks like this. This is a leaf. If I want to construct a tree with branches, I can put one branch to the left and another branch to the right. If I give this tree a name, then I can ask what's on the left and what's on the right, and what's the label. Of course, I could chain these attribute lookups and ask what is the root label on the left, and I would get the leaf value 1. Here's our old definition of fib tree. Fib tree takes in which Fibonacci number we want to construct. In this case, Fibonacci number 3 is the number 2, and it's the sum of 1 and 1, where this is Fibonacci number 2, and this is Fibonacci number 1. So we wrote this as a tree recursive function where we constructed the left and the right tree. If I wanted instead to write a Fibonacci binary tree, then I would simply have to change the fact that I'm constructing binary trees instead of regular trees, and when I call my constructor, I have to follow the arguments that are defined in the constructor for this class, which in this case are that you pass in the label, the left, and the right, and therefore we do not need these brackets. We just say, here's the left branch, and here's the right branch. And now when I compute a fib tree, I'll get a binary tree that doesn't have any brackets in it, because the list of branches is not part of this representation. There's always exactly 2 branches. And I can see Fibonacci number 1 on the left and Fibonacci number 2 on the right. Next, let's write a function that processes a binary tree. The contents function will take a binary tree t and return a list of all of the labels of t. If it's the case that t is btree.empty, the empty binary tree, then the list of labels contains nothing. Otherwise, we need to build a list of the contents of the left branch and the contents of the right branch, and also include the label itself. We have to pick an order. The order I'm going to choose is to list out the contents of t.left, and then include the label of t. And finally, include the contents of t.right. Let's check our recursive function. I'm passing in trees to a function that takes trees. What gets returned is always a list, so this will be a list, and that'll be a list, and so I'm adding these 3 lists together to get a longer list. Now, not only can I create fib tree for the 3rd Fibonacci number, but I can list out its contents. Everything on the left, followed by the label, and then everything on the right.